Now let us look at the next question. This is a passage based question. The passage is the beta decay process discovered around 1900 is basically the decay of neutron. In the laboratory, a proton P and an electron are observed as the decay products of the neutron. Therefore, considering the decay of a neutron as a two-body decay process, it was predicted theoretically that the kinetic energy of the electron should be a constant. But experimentally it was observed that the electron kinetic energy has a continuous spectrum. Considering a three-body decay process, that is, neutron decaying into proton, electron, and this is antineutrino. Around 1930, Pauli explained the observed electron energy spectrum, assuming the antineutrino to be massless and possessing negligible energy, and the neutron to be at rest. Momentum energy conservation principles are applied. From this calculation, the maximum kinetic energy of the electron is 0.8, that is, maximum kinetic energy of the electron is 0.8 into 10 to the power 6 electron volt. Okay, now the kinetic energy carried by the proton is only the recoil energy. Now let's look at the first problem. If the entry neutrino had a mass of 3 electron volt by c square, where c is the speed of light, instead of zero mass, what should be the range of kinetic energy of the electron? Now, in our assumption, neutron decaying into proton plus electron plus antineutrino. Okay. Now we assume that this is a massless particle, right? And it is having a negligible energy. So the total mass defect, total energy released, we call it as Q factor, is dependent on the mass defect. Okay, now as per the assumption, this has got no mass, and whatever mass defect is there will be based on the mass of neutron, proton and electron. So as per the assumption, delta M would be higher as compared to if we consider the mass of antineutrino as well. So if the products have more mass, then the mass defect would be lesser. Is that clear? So if mass defect, assuming that antineutrino has a mass, if the mass defect reduces by an amount of 3 electron volt by c square, therefore the energy of the reaction will also come down by an amount equal to 3 electron volts. Okay, because this difference in energy is equal to delta m c square. So the total kinetic energy that the electron can have will be now by, it will be slightly lesser by an amount equal to 3 electron volt. So the value was 0.8 into 10 to the power 6 electron volt minus 3 electron volt. Okay, so now the energy is slightly lesser, and this total energy will now get distributed between this and this, both electron as well as antineutrino. So the range of kinetic energy will be now, the least energy that it can have is 0, because if you assume that the entire energy is taken away by the antineutrino, then the energy of the electron would become 0, and it will be definitely less than 0.8 into 10 to the power 6, because now this kinetic energy is lesser by an amount of 3 electron volt. Okay, so option D is correct. Now the next problem based on the passage is, what is the maximum energy of the antineutrino? Okay, so the energy that antineutrino can have is 0.8 into 10 to the power 6 minus 3 electron volt. Okay, so this is the maximum energy that it can have if the energy of the, if you assume that the energy of the electron is 0. That means the entire energy or the Q factor value is taken up by the antineutrino, and the minimum energy that it can have is 0. Okay, so it will be, the maximum energy will be nearly this much, that means slightly less than this.